A system exhibits a convex response to perturbation when gains from favorable perturbations exceed losses from unfavorable ones of equal magnitude. This asymmetry is a structural property of the response function, not a statistical artifact of the environment. The curvature of the function determines whether variance is beneficial or harmful to the system. A convex response function accumulates value from perturbations. A concave one dissipates it. Optionality is the formal mechanism by which convexity is embedded into a system's architecture. Asymmetric exposure describes a system where the gain and loss functions are not mirror images of each other. A positively asymmetric system is bounded below, its downside is capped, while its upside scales with favorable perturbations. A negatively asymmetric system has unbounded downside and limited upside. The sign of the asymmetry determines whether variance in the environment is a structural asset or a structural liability. Systems designed without explicit asymmetry inherit the shape of their exposure from the environment by default. A system with a concave response function loses more from negative perturbations than it gains from positive ones of equal magnitude. This is negative asymmetry, and it defines fragility at the structural level. Under such a response, variance in the environment accelerates degradation faster than it creates benefit. The expected value of a concave function of a random variable is less than the function evaluated at the expected value. Fragility is therefore not a property of extreme events alone. It is present at every perturbation scale where the function is concave. The option payoff function takes the maximum of the input minus the strike and 0. This max operator is the formal mechanism that creates the absorbing floor in the response function. When the input falls below the strike k, the option is not exercised, and the loss is 0. When the input exceeds k, the full upside is captured and gain scales linearly with the input. The resulting response function is kinked, linear above the floor and flat below, which is the canonical convex payoff structure. Jensen's inequality states that for a convex function f, the expected value of f applied to a random variable is at least as large as f applied to the expected value. When f is convex, variance adds value. More dispersion in x increases EFX above FEX. When f is concave, the inequality reverses. Variance destroys value. This is the mathematical statement underlying the relationship between response function curvature and the value of volatility. System design choices that affect the curvature of the response function directly alter how the system relates to environmental variance. An option structure requires a floor that is maintained by design, a constraint, a reserve capacity, or a hard physical limit. If the absorbing failure state is reachable before the option can be exercised, the asymmetry collapses. Survival to the point of exercising the option is a necessary precondition for optionality to function as a design principle. A system that can be driven to an absorbing state before capturing any upside has no effective floor. Optionality without a survivable floor is not positive asymmetry. It is unprotected exposure to the worst case.